In this unit, we go about learning the process for naming alkynes using the standard IUPAC nomenclature, International Union of Pure and Applied Chemistry. So we're going to take a look at the guidelines for naming alkynes, and we'll do some example problems that illustrate that. So let's go ahead and get started. First thing to keep in mind is that the guidelines for naming alkynes are very analogous to the guidelines for naming alkenes, in that you're going to find the longest carbon chain that includes the alkyne group to form the parent name of the molecule. So what we'll do to name alkynes is we'll take the template that we used for naming alkanes back in chapter 3 and adapt that. So first off, to name alkynes, as I mentioned, you're going to find the longest continuous carbon chain, and it's essential that that longest continuous carbon chain be one that includes the carbon-carbon triple bond of the alkyne group. That's going to be what you use to form the parent name. The parent name of alkynes are going to end in the suffix YNE to designate that the molecule has an alkyne functional group. You will also need to indicate the numerical location of that alkyne group of the carbon-carbon triple bond, much like with an alkene, where you had to indicate where the carbon-carbon double bond was. So in addition to specifying the parent name here, right before the parent name, you do have to indicate the location, that is the carbon number, where the alkyne group begins. And there are a couple of different ways that you can go about doing that. You could either place the location of the alkyne group at the beginning of the parent name, so something like 1-hexyne would refer to a 6-carbon chain that had the carbon-carbon triple bond between carbons 1 and 2, or alternatively, this is synonymous with saying hex-1-ine to indicate that there is an alkyne group at carbon 1 of a 6-carbon chain. So after you've established the parent name of the molecule as the last part of the name, then what you're going to do is find out how you will go about numbering that parent chain, and you're going to always start numbering from the end closest to where the alkyne group is. So the alkyne group is going to take priority over alkyl branches and halogens in deciding how you start numbering the chain. So you'll start numbering from the end closer to where the alkyne group is. And if there's a tie, meaning that if the alkyne group is an equal distance from both ends of the chain, start numbering from the end closer to where a branch comes off. Then, once you have decided how to go about numbering the chain, what you're going to do then is look at the branches branching off of that parent chain and go about naming them using the same branch names as we've learned before, such as these names down here at the bottom are isobutyl, isopropyl, etc., etc. And you'll indicate where those come off of the parent chain, such as by saying that there is a 3-ethyl group coming off, or a 4-isobutyl group, etc. So let's go ahead and apply these rules toward naming an example of an alkyne. So here in the lower right, you'll see our example problem that we'll begin with. I encourage you to test your ability to go about naming the molecule on your own by hitting pause using the guidelines that we show here. We'll then go through the solution for this problem. Looking at the solution for the problem, remember that in the first step we want to find the longest continuous carbon chain that includes the alkyne group. So our longest continuous carbon chain that includes the alkyne group is going to run right through here. When we get to here, since going up or going down will lead to the same number of carbons in the longest carbon chain, we can go in either direction. We'll come up with the same name one way or the other. So now that we've come up with our longest carbon chain, the next step we need to do is number that longest carbon chain, beginning at the end closer to an alkyne group. So looking at this, if we start numbering from the right-hand end, that's going to put our alkyne group at carbon number 4. If we start numbering from the left-hand end of the chain, we'll find that our alkyne group appears starting at carbon number 3. So therefore, the numbering that I've shown in blue is the correct way to number, because that's going to put the alkyne group closer to the end of the chain. So I'm going to number this all according to the numbering that we started in blue. Okay, so our parent name therefore should be heptyne. So I went ahead and filled in the parent name is heptyne. We also need to specify where the alkyne group starts, because if we move the alkyne group from one carbon to another, it would create different constitutional isomers. The alkyne group starts at carbon 3, so we call this 3-heptine. Alternatively, you could also refer to it as hept-3-ine to put that number 3 as close to the ine as possible. They're remembering to separate numbers from letters using dashes. Now what we need to do, since we have the parent name in place here, is specify the name of any branches coming off that parent chain. So our parent chain is everything in green. We also have, coming off, this branch in pink. And so we need to specify that in the name of the molecule. It is a 2-carbon chain, so therefore it's referred to as an ethyl group. And so we'll go ahead and fill in ethyl. And the ethyl group comes off at carbon 5, so we call this 5-ethyl-3-heptine. Or alternatively, and just as good, 5-ethyl-hept-3-ine as the IUPAC name for this. Another thing that you should always be on the lookout for when you're naming molecules is stereochemistry. So we need to ask whether there's any chiral centers in here that we can specify as R or S. To specify a chiral center as RS would require that there be wedges or dashes attached to that chiral center. I don't see any chiral centers in this molecule, so no RS designation. The other thing to ask, are there any groups where we could assign the E or Z configuration? Remember that was the configuration that we would assign to alkene groups. So can we do something similar for alkynes? And the answer is no, because when we keep in mind the molecular geometry at the alkyne group, alkynes have sp carbons, and sp hybridized carbons are going to have a 180-degree ideal bond angle. And so as a result, of course, the molecule is linear at these 2 sp carbon atoms, and so there is no assignment of E or Z stereochemistry here. And that's going to be true for any alkyne group. Alkynes will never have assignment of stereochemistry to the alkyne carbon. So now let's do an example problem to illustrate these concepts that we've just talked about. We're going to provide an IUPAC name for the compound shown here. To test your knowledge, go ahead and hit pause, make sure that you can name this on your own, and get the same answer that I do. To name this, first things first, we find the longest carbon chain. So we're going to map out the longest pathway through the molecule. Don't be tempted to start here and go through the molecule. That's going to give a shorter chain than if we instead start here and make our way through the molecule. So go ahead, make your way through the molecule. When we get to here, you could go either up or down. It's going to give the same length of carbon chain and hence the same name one way or the other. So there's that. That's going to form our parent name. And thinking about our parent name, count out the number of carbons in this longest carbon chain, and that's going to give us the parent. We come up with 8 carbons in that longest carbon chain, so therefore the parent name is going to be octyne, which we'll fill in the prefix at the beginning here of what carbon number the alkyne group begins on. The other option is to refer to this as oct dash, and then we'll fill in with the number where the alkyne group starts, and then dash YNE as the parent name for this. So back to that topic. Okay, so now we need to decide how to go about numbering this so we can specify where the alkyne group is located. If we start numbering from the left-hand end, we see that our alkyne group begins at carbon number 4. If we start numbering from the right-hand end of the molecule, which I'll do in red here, we would see that our alkyne group would also begin at carbon number 4. So there's a tie here in terms of how to put the alkyne group as close to the end of the chain as possible. So in situations like that where we have a tie, what we would need to do is put the numbering so that a branch is as close to the end as possible. And numbering from the right-hand end of the molecule here puts a branch here, that blue methyl branch, at carbon number 2, whereas if we started numbering from the left-hand end, our first branch would not occur until carbon number 3. So therefore, the correct way to number this is using the red numbers. So we'll go ahead and fill in our full red numbering system, 1 through 8, matching up with the number of carbons in our parent. And that's going to result in filling this in as 4-octyne or oct-4-ine. Now our next step in the nomenclature process is specifying the names of the branches, which I've outlined in blue here. They happen to be 2 methyl branches, and so therefore we refer to it as a dimethyl group. Before we specify the term dimethyl, we also need to specify where those methyl groups are located. They're located at carbon number 2 of the chain and carbon number 6, so therefore it's 2,6-dimethyl, etc., or 2,6 dimethyl down here, directly connected to the term oct for ene. So that is going to specify the full structure of this constitutional isomer, but it's not giving us any information about the stereochemistry. So now we need to go ahead and fill in the stereochemistry at all relevant locations. And I see within this molecule one place where we could assign the stereochemistry with that dash showing up at carbon 6, and carbon number 6 is a chiral carbon. So let's go ahead and fill in the RS assignment there. Our highest ranked group is going to be the alkyne group. Remember that when you're assigning the rank here, if you have a carbon-carbon triple bond, that means that in thinking about the rank of that group, you're going to count each of those 3 bonds to carbon as 3 carbon atoms there. Coming on over, second highest ranked group is going to be the ethyl group, and the third highest ranked group is the methyl group. And then keep in mind that there is that hydrogen that's implied here that has to be on a wedge to fill in the last piece of the tetrahedron. So going from 1 to 2 to 3 is going to take us in the clockwise direction. And in this case, that is going to give us an assignment of S, because the hydrogen is pointed toward us rather than away from us. So you go ahead and put S in parentheses, and then dash 2,6 dimethyl 4-octene. You would also be welcome here to instead put in parentheses 6S, because it is at carbon number 6 where that chirality is. It's not necessary that you put the 6 in there though, since there is only one chiral center in this molecule. To follow up on this first question of providing the IUPAC name, as part B here, we'll ask that we provide the IUPAC name for the enantiomer of this molecule. Remember, the enantiomer is the mirror image isomer, and by definition, the mirror image isomer means that you've changed all the R's to S's and S's to R's to make the mirror image, but you've changed nothing else about the molecule. So therefore, the IUPAC name for the enantiomer here would just change that S at the beginning to an R. So it'd be R2,6, and we're just copying down everything else exactly like it was up top, 2,6 dimethyl 4-octene as a correct name for the enantiomer. This would be the only enantiomer of that molecule up top, because each molecule can have at most one mirror image, at most one enantiomer. Now, if we extended this into part C and asked the name of any diastereomer of this molecule, the answer would be that there are no diastereomers of this molecule, because the total number of stereoisomers, if we apply that 2 to the n rule, where n is the number of locations in the molecule that can have a stereochemistry of RS or EZ, would just give us 2 to the 1 rather, because there's only one stereocenter, one place where we could have RS or EZ. And so therefore the total number of stereoisomers is 2. We already accounted for those 2 total stereoisomers by describing the S configuration and the R configuration, those 2 enantiomers. So therefore, there are no diastereomers available here. So don't try to tempt yourself into thinking that there are.